Hello, my name is Michael McCabe, Product Manager for RFID at Pepperl+Fuchs. Welcome to part 5 of this series on IO-Link and RFID. In this video, now that we have our RFID hooked up to the IO-Link master and the IODD file has been uploaded, I'm going to review the two types of data that you'll be working with: service data, or ISDUs, and process data. I'll show you quick how to update a device parameter, and then I'll also go over the HTML document, which is basically a table that shows us where and how to update settings for our RFID head. And finally, to better understand that HTML document, I'll review some numbering systems like hex and binary, and finally, use all that information to restore the RFID head's factory settings. So first, it's important to know that there are two different types of data when dealing with IO-Link. Data that is sent continuously between the RFID head and a PLC, or let's say the web interface, and this is process data. And then there's data that is sent acyclically, or when you or something like a PLC asks for it. This is referred to as an ISDU, or Index Service Data Unit. And it's not hard to remember. Just think of the word service. It serves your request whenever you or a PLC asks, even during operation. So let's take a look at the web interface to see what this looks like. I go over to the Attached Devices tab, and then I click on the port my RFID head is attached to. And I'll let this screen load. And under the user role menu, which we're already on, we'll see the portions of the IODD which serve our requests. Again, instead of ISDU or Index Service Data Units, you may also hear the word service data. This layout is similar to a spreadsheet. These parameters and device info are uniquely indexed. There are main indexes and there are sub-indexes. So as we look to the next column, we're going to see information regarding what is stored in those indexes and sub-indexes and get descriptions about that data. So for instance, we will see the value, we'll see a description, whether that data is read-write or read-only, for instance, and more. So I'm going to scroll down to the bottom so that you can see the available rows. Some currently are collapsed. Now it does update faster, this web interface, if you don't keep every row open or expanded, so you can close the ones that you don't need. Now I will get into the options on this screen a little bit later on. Right now I'm just showing you how the user role menu is laid out. So at the bottom, I'm going to open up the ISDU command interface. And you see that on command, the RFID reader gets the device info that we're asking for, or sets a device parameter that we specify, all on command. Now of course, a PLC could also be sending or retrieving this data. The ISDU command interface in the web interface is just one way to do it. Again, we send these commands acyclically, which is fancy for saying whenever we or the PLC wants. It's not cyclic like the process data. So speaking of process data, where is it? Well, I'll go to the dropdown and select process data. Take note that 1 equals yes and 0 equals no. Now what is shown is correct with my current setup: 0 reads and 0 writes. There has not been a read or write done. Now this is because number 1, I don't have a tag near my RFID head, even though the RFID head is actively trying to read. That's why there's a 1 next to task active. And again, the active read task is process data. It's occurring cyclically. It's trying to read every so many milliseconds. And 2. There are 0 write successfuls because I haven't told the RFID head to write to a tag. And real quick, if I scroll down, in the output process data section, 1 now equals execute. You can see I've not executed a command to read or write, and even if I did, I didn't tell it what data to write to the tag. Again, this is all what I'd expect. So let's do a simple example to better understand each type of data. By default, this RFID head is set to auto start. With this enabled, as soon as it's powered up, it starts actively trying to read. Remember that when a task is active, the blue light on my RFID head will be lit. So for this example, let's turn off auto start. So let's go find that auto start parameter setting in our table. Let's head back over to the user role menu. Remember, this service data is indexed. So if I scroll down, auto start is indexed under 204 with subindex 4. Thanks to the IODD file, the web interface tells us if we change the data in this indexed location from 80 in hex to 00 in hex, auto start will be turned off. So the RFID head won't actively start trying to read when it's powered up. So let's do that now. So I'm going to scroll down to the bottom and open up the Isdu interface. Again, this is where I can set a command. Let's type in 204 for the main index and 4 for the subindex. And I'll type in the hex command of 00. This Isdu interface always uses hexadecimal, at least for now. I'll click set, and we see that the command has been executed. So we just performed an acyclic command. It serviced our request. Now, you can't see it, but the RFID head's blue light did just turn off. It's no longer trying to read since we turned auto start off. And auto start will remain off when the RFID head is powered up again. You could even connect the RFID head to a different port, and this setting can remain the same. As a side note, if you upload an IODD file for, let's say, this RFID head, the IODD file will be available to any port the RFID head is connected to. You don't have to upload an IODD file for each port, just each device. And again, just to prove to you that I made this change, so not only can I refresh the screen and then look for that change, it'll just take a second to refresh. And we see that change right here. But let's look at the process data, which remember is our other type of data. And we see that no task is active, indicated by a 0. That is correct. Now real quick, let's turn back on auto start. I'll head back over to the user role menu. I'll wait for it to load. And this time, I'm going to take a slightly easier path. Thanks to the web interface, I can also update device parameters simply by clicking Edit. I scroll down to Auto Start and select 80. The H stands for hex. And I click Save. Easy as that. Now you may be wondering, why didn't I just do that before to turn off Auto Start? Well, because I'm just giving you an example of different ways that we can update our RFID's settings or parameters. Also, clicking Edit and choosing dropdowns won't let you do everything. You will need the ISDU interface for some things. For instance, as you'll see in the next video, it's where we'll type in the data that we want to write to our tag. Also, I do want to get you familiar with noticing that the parameters are indexed in certain locations. This will help you understand the HTML document when I show that to you. And you can better understand what PLCs are doing when looking for and updating data. They're kind of doing what we just did. And really, I could have picked any setting to demonstrate. I just thought that the auto start feature was a good place to start. Now, I said in the first video that the web interface is a great tool for demoing, but it won't show you how fast we can read and write to a tag. The web page is only updating about every 15 seconds. So now I'm going to prove that the RFID head is reading. So I'm going to head back over to the process data. As soon as I place a tag in front of the reader, the orangish yellowish LED lights up. Now I can either wait for the web page to begin updating, or I can click refresh, which I'll do now. We see a 1, which means yes, a read was successful. And if I look down here, I see an 05, which tells me two things. Again, that the read was successful, and a read task is still active. Now here's a question. How do I know what that 05 indicates? Well, that's a good question. You could look it up in the manual, but remember, there's a lot of information in the IODD file. And it's the folder that actually doesn't have Pepperl+Fuchs in the name. So let's look in here and see if anything tells us what the 05 means. So by now, we know that the IODD file helps us visualize the device parameters and process data when using the web interface. And in the IODD file, it's the XML file that's mainly needed to do this. So let's open that up and see if it helps. Well, this certainly doesn't look easy to read. An XML file is just used to describe data, to carry it, not visualize it. Fortunately, I can convert this to an HTML document, which does do a great job helping to visualize information. When you think of HTML, think of all the internet web pages that you're used to and how easy it is to view information there. You could use an IODD viewer to convert it, but fortunately, I already have it since I downloaded the IODD file from Pepperl+Fuchs website. So let me back out of this folder and select the folder beneath it. If you want the English version, make sure to click on the one that has EN in the title. Let's open and take a look. Now, these blue boxes at the top go over some of the device information, most of which we've already covered in recent videos. So let's scroll down to the next section. If you remember, we're trying to figure out what that 05 meant in the process data section. Fortunately, this first section describes the process data or cyclic data. Now you may ask, does this HTML document also cover the ISDU data, which we talked about before? Yes, it does. So let's scroll down past the process data, and here we see the beginning of that service data. Notice the main indexing. The process data above shows sub-indexing, but not this main indexing. But for the meantime, let's go back to the process data. Remember, I said 05 indicates that a read was successful and that a task is active. And I see that here. First, the above red block sub-index 1 is the same as this red block. Again, sub-index 1. And we see it means a read was successful. And then in this yellow block, sub-index 3, which again is the same as the yellow block below, indicates that the task is active. Now, you may be asking, but how does that 05 in hex correspond to this? Well, it does, and if it's not clear, it's because we need to know that we're basically dealing with different numbering systems. So if you're only used to decimal, 1, 2, 3, 4, 5, 6, the system that most of us grew up with, you'll need to switch your thinking over to binary or hexadecimal. These are just two other methods for displaying numbers. So for instance, here is the number 247 in the decimal numbering system. You're used to seeing numbers like this. The binary system can display any number you can think of using only ones and zeros. This is great for computers because they mostly get data from lots of switches that are either on or off, 1 or 0, true or false, high or low, whatever you want to call it. It's essentially saying the same thing. So here you see 247 in binary is represented as 11110111. And last, the hex system is great because it lets us display large numbers with less digits. And again, our 247 displayed in hex is F7. I can say that I have 247 apples, which is the same as saying I have 11110111 apples, and it's also the same as saying I have F7 apples. So again, I want to prove to you that 05 in hex is actually telling me that a read was successful and that a task is active. Well, I'm getting there. Just a couple more things to explain though first. So on the process data screen, here you see 05 in hex represented as 0x05. The 0x is just a prefix that identifies a number as hex. This would be the same as if you saw a B before a binary number. On the screen, you see how this would look on the number 247. And so now, since it's easy, let's go to an online converter and look at 05 in other numbering systems to see if we can't get some help. Alright, let's type in 05 into the hex field and click convert. And what we see is that 05 in hex actually equals 5 in decimal. Again, the base 10 numbering system that we're all familiar with. And also, we see that it equals 00000101 in binary. Alright, so at this point, to show you how 05 in hex gives me the information I was telling you about, I'll first go the easy route. I'll bring back up my HTML document and let you know that when looking at this, we should be thinking in terms of the binary numbering system. And this does make sense after all. This sheet shows us how the PLC, IO-Link master, and IO-Link devices communicate with one another, again using electronic communication, so ones and zeros. So remembering that 05 in hex equals 0000, 0101 in binary, if I overlay that onto my HTML document, and remember that 1 basically equals true and 0 basically equals false, it's telling me that subindex 1 and subindex 3, again seen here in red and yellow, are both true. Looking above, these correspond to read successful and task active. So that's how I knew just by seeing 05 in hex that these conditions were true. Easy as that. But here's the weird part. Why 05? I just said that subindex 1 and subindex 3 are indicated as true. If I add those together, that doesn't equal 5, does it? This is where we need to know a little bit of theory about numbering systems to know what's going on. Well, let's go back to our example from before and realize that a decimal system is a base 10 system. Deci basically means 10. So I've added 10 to the power of 0 below the 7. 10 to the power of 0 is equal to 1. So there are 7 ones. 10 to the power of 1 is 10. So there are 4 tens. And 10 to the power of 2 is hundreds. So there are 2 hundreds. So when I add them all up, you get 247, just like we saw before. This is a similar idea to the binary system, but instead of using a base 10 system, it's a base 2. So instead of taking 10 to the power of something, we take 2 to the power of something. Instead of the 0 through 9 digits representing ones, tens, hundreds, and thousands, and so on, we get 0 to 1. We have 2 digits to work with, and they represent 1s, 2s, 4s, 8s, 16s, and so on. So this means in our example that we have 1, 1, and we have 1, 4. So 1 plus 4 equals 5. So again, the decimal system is base 10 and it has 10 digits. The binary system is base 2 and it has 2 digits. And if you're already thinking ahead, yes, this is the same for hexadecimal. It's a base 16 system and there are 16 digits. If you're saying, but there are only 10 numbers that I know of, how do you get 16 digits? Well, you do by using letters. That is why you see 0 through F. Highlighted in gray are the 16 hex digits, and below you see their decimal equivalents. You can see here that my 5 in decimal is represented the same as 5 in hex. But 13, for example, is represented as D. So to convert the C1A2 hex number you see there to a decimal number, I'll add together 2 times 1. This is in the least significant bit location. A, or 10 times 16. 1 times 256. And C, or 12 times 4096. I add all those up and I get 49,570. So anyways, that's how I know that this 1, or the least significant bit, actually equals a 1. And this bit is actually equal to a 4. So I add 1 plus 4, and that's why this group of 8 digits is essentially equal to 05, or 5 in decimal. Which again, I see right here. And just so you know, each one of those zeros or ones can be referred to as a bit. And 8 bits make up a byte. Or as we see here, an octet. 1 byte can be represented by a 2-digit hex number. In essence, these 4 bits make up the 0 in our hex number, and these 4 bits make up the 5 in our hex number. Now, take a moment to notice in this section, each row equals an octet, and each box represents one of its 8 bits. And these bits work great for these first 4 pieces of data: read successful, write successful, task active, and error. And all of these questions can be answered with a yes or no, true or false, 1 or 0. And that's why the data is specified as Boolean. Boolean is just another way of saying ones and zeros. Again, each 1 or 0 is telling the PLC or web interface something, some piece of information. But what if it's not a simple yes or no question? Well, we just use a combination of ones and zeros to answer. And that's what you see in sub-index 5 under octet 1. The data type is specified as an 8-bit integer. It's asking how many bytes of data should be read when the tag is in front of the RFID reader. So, to answer this question, we'll just look at the combination of these 8 bits and what they're telling us. Looking back at the process data, we see that the second byte, or octet 1, is shown as 08. So that means the RFID head will read 8 bytes of information from the tag. Here, you can see what 08 in hex equals in binary. You'll notice that the 1 is in the 8 spot of the binary system. By default, the data length in easy mode is set up for 8 bytes. Something I haven't talked about yet is this RFID head can be operated in either easy mode or expert mode. 90% of the time, your applications can be covered with easy mode, and it allows up to 28 bytes of read-write data and requires no additional function blocks to operate. Function blocks are needed for expert mode, which is capable of transmitting much more data at very fast speeds. Again though, easy mode is easy and a great choice for most applications. So this is why in sub-index 6, seen in the light blue color, there's a 28 octet string that will be used for the read data. These are available to you in easy mode. And I can see this if I just scroll down. Octet 2 and octet 3 aren't used for anything, and that's why we see slash marks here. But after that, we see the same light blue color with a 6 for octets 4 through 31. These are the 28 octets or bytes which can be read off the tag. So hopefully this all makes sense now. When looking at our process data, taking a quick look at the HTML document tells us by the first byte that the read was successful and that the read task is active. The second byte lets us know that I'm only currently asking for 8 bytes of data. Again, even though there are 28 available to us in easy mode. Bytes 3 and 4 aren't in use again, that's why we saw those slash marks. And of course, these are the remaining 28 bytes. It's the data available to the user, again in easy mode. The first 4 bytes again, just being header information. And just to clarify, the web interface is going to show all 28 bytes of read data even if you're working with less bytes. For example, your tag may actually have data in all 28 bytes. But if you say only read the first 8 bytes, you'll see only the data in those first 8 bytes. The remaining bytes will just display placeholders shown as 00, seen here. It's only going to retrieve or write what you ask it to. Well, we just looked at one of the process data sections on the HTML document. And if you remember, this is cyclic data. Data that's communicated basically back and forth on a continuous cycle. But if you remember, there is also service data, which lets us initiate a command or set a device parameter whenever we or the PLC wants. So at this point, before I move on to the next video, I'd like to reset my RFID head just to make sure that I'm working with the default settings, basically a clean slate. We're currently looking at the process data, but I need to find the service data because I want to initiate a command. So I'll scroll down. These first 2 indexes, 0 and 1, describe the IO link device's direct parameters. These are basically the bare bone pieces of information an IO link device should have. Some companies that make very simple and cheap sensors may choose to only provide this information in addition to the process data. But the RFID head that I have hooked up provides many ISDU options, and that's what I'm looking to reset. So these options begin around index 2, and if you keep scrolling down past index 2, you'll start seeing the other options that can be changed. These are ISDUs. They service your commands. So whether that's changing the product name to something else, or changing the RFID head from easy mode to expert mode, this is where on the HTML document that you can find this information. So back up to index 2, And here, I see the command that will let me restore the factory settings for those ISDUs I just mentioned. To make this happen, I need to enter 130 into index 2. But again, it needs to be in hex. So I'll type this into the online converter, and I see that 130 in hex is 82. So back to the web interface, I'll type in this information, hit set, and we see command executed. This means my RFID head has just been set back to its default settings. And just to reiterate what we just reset, it's things like whether auto start mode is on, or how many bytes of data are read. Basically, the value specific to the RFID head, not the IO-Link master. So for instance, if you set up a different IP address for your IO-Link master, what we just did won't change that. Alright, in the last video, I'm going to show you how to more specifically read and write to a tag, and discuss some of the other settings and information shown in the user role menu and the process data section. Again, my name is Michael McCabe, Product Manager for RFID at Pepperl+Fuchs. And as always, remember that Pepperl+Fuchs is a leader in industrial automation. So click the subscribe button below to see the new industry-leading products that we come out with. And if I did a good job on this video, please click that thumbs up button so others can find it more easily. Remember, if we don't tell YouTube what's important by giving it a thumbs up, we're going to keep seeing only those shocking and crazy videos which can be fun, but they're not helping us to become the intelligent professionals that we aspire to be. Thanks, and I'll see you next time.